Today we'll begin our discussion on the functional group amines. Amines are organic nitrogen compounds. There's a number of biologically active amines, some of which are shown here. These include cocaine, nicotine, mescaline, and morphine. Alkaloids are a family of important biologically active amines. Most of them are synthesized by plants, and their role is to protect them from being eaten by insects and other animals. Okay, many drugs of addiction are classified as alkaloids. Some other examples of biological activities of amines include dopamine, which is a neurotransmitter. Epinephrine is a bioregulator. Niacin, vitamin B6, is an amine. Other alkaloids, as shown on the previous page, include nicotine, morphine, and cocaine. And of course, amino acids, the building blocks of proteins. We can classify amines according to the number of carbons that are directly attached to the nitrogen. If we begin with ammonia and we replace one of the nitrogens with an alkyl group, then we have a primary amine. If we replace two nitrogens with alkyl groups, we have a secondary. 3 gives us a tertiary. And there's a fourth class, which is called a quaternary, in which we have 4 alkyl groups. Now, when nitrogen has 4 bonds, then it'll bear a positive charge, and there'll be some counteranion with it. Okay, so here we have a primary, a secondary, and a tertiary amine. Okay, this one would be called propylamine, or in the IUPAC, it would be propan-1-amine or 1-propanamine. This one is diethylamine. In the IUPAC, it would be N-ethylethanamine. And then this is methyl diethylamine. It's a tertiary amine. And in the IUPAC, this would be N-methyl N-ethyl ethanamine. Many amines are known by their common names. We simply name the alkyl groups. Okay, here we have ethylamine. Here we have diisopentylamine, diethylmethylamine. Okay, this is a tertiary amine. And then here's a quaternary salt. This is tetrabutyl ammonium chloride. Okay, this is cyclohexyl dimethylamine. This is benzylamine. It's distinct from aniline. Okay, aniline has the NH2 directly attached to the benzene ring. Okay, here we have diphenylamine. Okay, when an amine is a substituent, then it's an amino. Okay, so here we have 3-aminocyclopentene. This is the IUPAC in parentheses, cyclopent-2-ene 1-amine. Gamma-aminobutyric acid, also called GABA, it's also a neurotransmitter. Its IUPAC is 4-aminobutanoic acid. Okay, we'll talk about carboxylic acids in the next chapter, but carboxylic acids have the highest priority. So the carboxylic acid group is automatically on carbon number 1. Okay, here we have trans 3-aminocyclohexanol. Okay, the alcohol takes priority, so it's automatically on number 1. Okay, make sure you don't call this a phenol because it's a cyclohexane. Okay, this is This is p-aminobenzoic acid, also called PABA. This used to be used as a sunscreen. For the IUPAC system, the name is based on the longest carbon chain, and the suffix is amine. We drop the E from the alkane name and replace it with the suffix amine. Substituents on the nitrogen will have a capital N prefix. Okay, so here, the longest chain is 5. Okay, so that's pentane. And this is pentan 1-amine, and the bromo is on carbon number 3. So this is 3-bromo 1-pentanamine, or pentan 1-amine. Okay, the longest chain here is 6. The amino group is on carbon number 3, and so we would name this as capital N dimethyl 3-hexanamine. Okay, every substituent gets a locant. Okay, here are some aromatic amines. Okay, aniline is aminobenzene. Okay, here is 2-ethyl-aniline. Here the amino group takes priority over the alkyl group. And then this would be NN-diethylaniline. Okay, remember the multiplier prefix and the fact that every substituent gets a locant. Okay, and then this is 4-methylaniline, or p-toluidine, as it's commonly called. Okay, here are some heterocyclic amines. Aziridine, this is pyrrolidine, which has the fully saturated ring. For a substituted pyrrolidine, nitrogen is on position number 1. Okay, so this is called either 1-methylpyrrolidine or capital N-methylpyrrolidine. Okay, here we have imidazole. The nitrogen with the H is position number 1. Okay, we go around to the other nitrogen. Okay, here is indole. And again, the nitrogen with the H is position number 1. Here's pyridine. The nitrogen is position number 1. As you can see in the next example, 2-methylpyridine. The fully saturated 6-membered ring is called piperidine. If we have two nitrogens at the 1 and 3 positions, then that's pyrimidine. And then the last one is purine. Pyrimidine and purine are both important components of the bases that occur in DNA and RNA. Amines have a trigonal pyramidal structure, like ammonia. The lone pair exhibits a repulsive force, and so that's why the amines are not planar. Here's an electrostatic potential map for trimethylamine. Okay, you can see that the electron density is concentrated near the lone pair, whereas the methyl groups are electron deficient. Okay, the angle for many amines is typically less than 109.5 because the lone pair takes up a lot of space. Okay, in this molecule, if it were frozen in place, it would be chiral because we have 4 different groups. This would be non-superimposable on its mirror image. But in fact, what happens is that we have rapid inversion that takes place. Now, in the case of phosphorus, which is just below nitrogen in the periodic table, you typically don't have this rapid inversion. And if you have three different groups on a phosphorus and a lone pair, then typically you have chirality. Okay, in this example, we have a chiral compound. We have two mirror images, but it's not the nitrogen, it's the carbon that is chiral. Chirality is possible on nitrogen if we have, instead of three different groups, we have four different groups, such as in quaternary salts. And this turns out to be an important method of separating enantiomers. Okay, we can make chiral salts, diastereomeric salts, and then separate them, either by crystallization or some other means. Okay, here inversion of configuration is not possible since there's no lone pair. There's four covalent bonds. Okay, in strained cyclic compounds, heterocyclic compounds in which there's a nitrogen, okay, inversion is not possible. And in this example, R122-trimethylaziridine, you don't have this inversion that takes place. Also, let me go back to the structures of the alkaloids here early on. Okay, if you look at, for example, morphine and cocaine, okay, here it's not possible to invert, and this is especially true if the nitrogen is at a bridgehead. Okay, what about some of the physical properties? Amines that have a hydrogen bonded to the nitrogen do exhibit hydrogen bonding, and hydrogen bonding can raise the boiling point. The NH bond is not as polar as an OH bond, and so the hydrogen bonds are not as strong, but they certainly do have an influence. In the case of tertiary amines, you only have hydrogen bond acceptance, not donation. With primary and secondary amines, the nitrogens can act as both can act as donors, and the hydrogens can act as acceptors. Okay, if we consider solubility and odor, small amines, okay, up to 6 carbons are soluble in water. And like most organic compounds, the more carbons we add to the chain or to the molecule, the less soluble in water it becomes. All amines accept hydrogen bonds from water and alcohols, okay, whether they're primary, secondary, or tertiary. Branching actually increases the solubility, and most amines will smell like rotting fish. Okay, this is a compound called 1,5-pentane diamine, or 1,5-diaminopentane. It's commonly called cadaverine, and it's given off from rotting flesh. There is a similar molecule, which is the 1,4-diaminobutane, which is called putrescine. And likewise, it has an extremely bad odor. Okay, this is an important point in this chapter. Amines are basic. Okay, they act as weak bases. The lone pair of electrons on nitrogen can accept a proton from an acid. Aqueous solutions of ammonia and other amines are basic to litmus. That is, they'll turn litmus blue. Ammonia has a pKb of 4.74. Okay, it is a weak base. Alkyl amines are typically stronger bases than ammonia. And increasing the number of alkyl groups decreases the solvation of the ion. So secondary and tertiary amines are actually similar to primary amines in basicity. Okay, so while the alkyl groups are electron donating and would tend to increase the basicity, we also have to consider solvation effects. Okay, there's two main ways that amines react. They can react as nucleophiles. Okay, they're good electron pair donors. And here we have an SN2 reaction where the amine replaces the leaving group, the iodine. Okay, this produces an amine salt. Okay, because now we have 4 bonds to the nitrogen, so it'll carry a plus charge. Amines can also act as proton bases. Okay, if we have an acid, HX, okay, something like HCl, the nitrogen will grab that hydrogen, and again, we'll get an amine salt. Okay, we can quantify how weak or strong a base is using this equilibrium constant called the Kb. And here we have an amine reacting with water to form the ammonium ion and hydroxide. Okay, so any equilibrium constant is products over reactants. We omit the water from our expression, so it's RNH3 plus times OH minus over the undissociated base. Okay, that's the Kb value. The pKb is minus the log of the Kb. Okay, here alkyl groups stabilize the ammonium ion, and they'll make the amine a stronger base compared to ammonia. Okay, so here we have the effect of a methyl group. The methyl group is pushing electrons toward the nitrogen, and so we can see that methylamine is more than 1 pKa unit less than pKb, unit less than that of ammonia. So that means that this is more than 10 times stronger as a base. Okay, what about resonance effects? Okay, in the case of aniline, the lone pair on the nitrogen donates electrons into the ring, so we have a number of resonance structures that can take place. Okay, this actually weakens the basicity because the nitrogen is less able to donate its lone pair to a proton. Okay, it's because it's also donating it into the ring. Okay, and once we protonate the nitrogen, that disrupts the ability to induce resonance stabilization from the nitrogen. Okay, so as a result, aniline is quite a bit weaker as a base than is, say, methylamine or ammonia. In the case of perol, we discussed this in terms of aromatic compounds. Perol is an aromatic compound, and if we were to protonate the nitrogen, that would disrupt the aromatic system, and that would be very unfavorable. Okay, so here, the pKb of perol is 13.6. And for the protonated perol, it's 0.4. Okay, think about acetic acid, which is about 4.7. So this is more than 10,000 times more acidic than acetic acid. Hybridization can also affect basicity. Okay, if we compare pyridine with piperidine, in pyridine, the nitrogen is sp2 hybridized, and so it's less basic. Whereas in piperidine, it's more basic. It's sp3 hybridized. Pyridine is less basic than aliphatic amines, but it's more basic than perol because it actually doesn't lose aromaticity when it gets protonated. Okay, this lone pair is not part of the aromatic system, unlike perol. Okay, so that's a difference of roughly 6 pKb units. So this is about 1,000,000 times more basic than pyridine. Piperidine is about 1,000,000 times more basic than pyridine. All right, ammonium salts are formed when amines react with acids such as HCl. Okay, this changes some of the properties. For example, large amines are typically water insoluble. Okay, but when we make the amine salt, since it's now ionic, it's water soluble. Okay, this reaction is reversible. We can convert the amine salt back into the free amine using sodium hydroxide. These amine salts are ionic solids, so they typically have high melting points. The amine salts are soluble in water. Okay, they don't have a fishy odor. Okay, this has practical significance. For example, when you eat fish, you might add tartar sauce or malt vinegar to it. The tartar sauce has vinegar. You might also add lemon juice. Okay, these are acetic acid, citric acid, or weak acids, which will neutralize the amines and counteract that fishy flavor. Okay, there is a Scandinavian dish. It's called lutefisk, in which the fish is actually cured in lye, which is a base, and this makes for a stronger odor and flavor. Okay, this acid-base property and differences in solubilities is important in being able to separate amines from other organic compounds in the laboratory. Okay, if we have the free amine and other organics, say, dissolved in ether, one of the things that we can do is we can use aqueous dilute HCl as our water phase. We put that in the separatory funnel. We form the amine salt, which is now water soluble, and the other organics, which don't contain basic groups, will remain in the ether layer. All right, then we can remove the ether phase, and if we add NaOH, we can regenerate the free amine. Okay, so this allows us a way of separating amines from other organic compounds. Okay, here we have what's called phase transfer catalysis. Back last semester, we talked about the alpha elimination reaction in which we take hydroxide and chloroform or trichloromethane. This generates a dichlorocarbene, which adds across the double bond. The carbene accepts a pair of electrons and it donates a pair of electrons to form this cyclopropane ring. Okay, the problem here is that chloroform and cyclohexene are not soluble in water. Okay, but if we use a phase transfer catalyst, okay, here we have tetrabutyl ammonium chloride, in which we have an anion exchange. The hydroxide replaces the chloride. Here we get a tetrabutyl ammonium hydroxide salt, okay, which is now soluble in organic liquids. And okay, because of the greasy butyl groups, we can dissolve it in an organic solvent, and then the hydroxide ion goes along in order to keep the charges balanced. So we can carry this reaction out in an organic solvent. Okay, a number of illegal drugs, okay, such as cocaine and heroin, contain basic amino groups. Okay, there's also a number of prescription and over-the-counter drugs. In fact, many prescription and over-the-counter drugs which contain the amino group. Some examples include Benadryl, which is diphenhydramine hydrochloride, Dimetap, which is bromophenyramine maleate. Okay, these are amine salts, and there's two reasons why these are converted to the acid form, to the salt form. One is the salt is more water soluble. The second reason is that there's no fishy odor. Okay, if we were to take some of these over-the-counter allergy medicines and convert them to their base form, many of them would actually smell fishy. Okay, here is cocaine, and cocaine contains a basic nitrogen. And these two forms can be interconverted using HCl, and NaOH or sodium bicarbonate, which is baking soda. Cocaine is usually smuggled and snorted as the hydrochloride salt. Okay, the reason for that is that the hydrochloride has less odor. It's more difficult for drug sniffing dogs to detect. If the cocaine hydrochloride is treated with sodium hydroxide or baking soda and then extracted, that converts it back to the free base, which is the form that's used for smoking. When the free base is heated, it forms a cracking noise, and that's the reason why it's called crack cocaine. Right, let's turn to the spectroscopy of amines. Okay, here we have an infrared spectrum of propylamine, or 1-propanamine. This is a primary amine. It has 2 NH bonds, and we'll see 2 NH stretches. The reason we see 2 bands is because we have a symmetric stretch and an asymmetric stretch, where the 2 NH bonds are stretching in unison, or if they're stretching asymmetrically. Okay, if we have a primary amine, as shown in this spectrum, we'll see 2 NH stretches. Okay, these will occur around 3,300 wave numbers. If we have a secondary amine, we'll just see 1 stretch. If we have a tertiary amine, there'll be no NH stretch because there's no NH bond. Okay, in the proton NMR of amines, the alpha carbon is affected by the nearby nitrogen, and so we see a downfield shift, not as much as with an oxygen or a halogen, okay, which is usually down to about 3 or 4. This is about 2.5, 2.6. The amino protons themselves can be highly variable. Okay, in this particular experiment, they showed up at 1.7, but they can be highly variable depending on temperature, solvent, concentration, etc. Okay, this is 1-propanamine again. Okay, the NH2 appears as this very broad peak. The alpha hydrogens, the ones next to the nitrogen, are the most downfield. Okay, downfield is to the left. This shows up as a triplet, okay, because there's 2 neighboring hydrogens. Okay, remember the n+1 rule. Okay, the protons that are farthest away on carbon number 3, okay, those are the most upfield. Okay, those also show up as a triplet. And those on the beta carbon, carbon number 2, okay, they're split by the hydrogens on carbon number 1 and on carbon number 3. Okay, up above the proton spectrum, we have the carbon 13 spectrum. There's 3 different carbons, and so we see 3 different peaks. Okay, this was done in deuterochloroform as a solvent, and so that's what this peak at 77 is. Okay, in mass spectrometry, the most common form of fragmentation occurs by what is called alpha cleavage. That's where the bond breaks between the first and second carbon attached to the nitrogen. Okay, the reason for that is that it gives us a resonance stabilized iminium ion. Okay, so here we have butylpropylamine, and the most common cleavage occurs between the alpha and beta carbon. Okay, so we'll see fragments at 72, for example. We'll we'll see another fragment at 86. Okay, so here's butyl propylamine, 72 and 86. Those fragments occur because of alpha cleavage. Okay, I'm going to stop here, and we'll pick up the rest in a separate